So the problem states that a 15 millimeter diameter mild steel sphere K equals 45 watt per meter degree Celsius is exposed to cooling airflow at 20 degrees Celsius, resulting in a convective heat transfer coefficient H equals 120 watt per meter square degree Celsius. Determine the following. A. Time required to cool the sphere from 550 degrees Celsius to 90 degrees Celsius. B. Instantaneous heat transfer rate 2 minutes after the start of cooling. Okay, for mild steel, you can take the density rho as 7,850 kg per meter cube, specific heat Cp as 475 joule per kg degree Celsius, and alpha as 0.045 meter square per hour. So these are the data given here. With this data, we need to find out the time required to cool the sphere from 550 degrees Celsius to 90 degrees Celsius and the instantaneous heat transfer rate after 2 minutes from the start of cooling. So here what we have is we have a sphere, we have a mild steel sphere of 15 mm diameter. So we have a sphere here. This is having a diameter of 15 mm and this is made up of mild steel. And this is exposed to cooling air at 20 degrees Celsius. So it is surrounded by cooling air which is at 20 degrees Celsius, and the heat transfer coefficient between these two, that is the surface and the air, is 120 watt per meter square degree Celsius. Okay, this is the heat transfer coefficient. The thermal conductivity of the sphere is given and the diameter of the sphere is given. Now we need to find out if the mild steel sphere was at 550 degrees Celsius initially, how long will it take to reach 90 degrees Celsius? That is, from 550 degrees Celsius, it has to reach 90 degrees Celsius. For that, we need to find out the time. And then we need to find out the instantaneous heat transfer rate, Q instantaneous, after 2 minutes. So these are the two things which we have to calculate. First, let us list out the data. We have the diameter of the mild steel sphere. So diameter is 15 millimeter. Then we have thermal conductivity. So K equals 42 watt per meter degree Celsius. Then we have cooling air temperature. So that will be our TA. TA is 20 degrees Celsius. And we have the heat transfer coefficient H. So H is 120 watt per meter square degree Celsius. And now we need to calculate two things. A, tau, that is time, has to be calculated if the initial temperature of the sphere is 550 degrees Celsius and T tau, that is the temperature at which we need to calculate the time, is 90 degrees Celsius. So for these two conditions, we need to find out the time required. Then B, we need to find out Q instantaneous if tau equals 2 minutes. 2 minutes is nothing but 120 seconds. So after 120 seconds, we need to find out what is the instantaneous heat transfer rate. So the other properties of the mild steel, are given as rho equals 7850 kg per meter cube. Then Cp equals 475 joule per kg degree Celsius and alpha equals 0.045 meter square per hour. Okay, these are the data given. Now, first thing is we need to decide whether we can solve this problem using the lump system analysis or not. So for that, we need to calculate the Biot number. So whenever you are solving any transient conduction problems, the first and foremost thing which you have to do is to find out the Biot number with the given definitions. So the Biot number Vi will be equal to, we know the formula, it is H into Lc divided by K. And we are dealing with a sphere here. So this is a sphere made up of mild steel. So for that, for sphere, Lc will be equal to, we know that it is R by 3. For a long cylinder, it is R by 2. For a sphere, it is R by 3. So now we need to find out the radius. Here they have given the diameter, so we need the radius. So I can write, so radius will be equal to diameter by 2, which is 15 millimeter divided by 2 is 7.5 millimeter. So the characteristic length will be equal to 7.5 into 10 to the power of minus 3 divided by 3.
So 2.5 into 10 power minus 3.
Okay, it's 2.5 into 10 to the power of minus 3 meters. So this is the characteristic length. Now let us substitute that and find out the Biot number. We know K, we know H. So let us substitute this and find out the Biot number. The Biot number Bi will be equal to, H is 120 into characteristic length Lc is 2.5 into 10 to the power of minus 3 divided by K is 42.
7.1428 into 10 to the power of minus 3.
Okay, 7.1428 into 10 to the power of minus 3. Okay, since the Biot number is, if I write this in terms of regular numbers without 10 to the power of minus 3, it would be 0.00711428, which is less than 0.1. Okay, since the Biot number is less than 0.1, we can go for lump system analysis. So once we calculate this, we need to write a statement. Since Biot number is less than 0.1, lump system analysis can be applied. So now I know that for a lump system analysis, theta by theta I will be equal to e to the power of minus tau by t. Let us calculate t so that the same t can be used for both the cases. So t is given by rho Cp into Lc divided by h. I need to remember these equations. Density, so density here it is given as 7850 and Cp is given as 745 joule per kg degrees Celsius. So it is 7850 multiplied by 475 into characteristic length is 2.5 into 10 to the power of minus 3 divided by h is 120. Calculate the value of t.
77.68.
77.68. The unit will be seconds. That's why we call it as time constant. Now let us solve for case A. So A, we need to find out tau. If Ti is 550 degrees Celsius and T tau is 90 degrees Celsius, right? That is the condition. Yes. This is the condition. We need to find out the time. if the cooling starts from 550 and ends up at 90 degrees Celsius, what is the time taken for the cooling from 550 to 90 degrees Celsius? So for that, so now let us use this equation. Theta is T tau minus Ta divided by theta I is Ti minus Ta will be equal to e to the power of minus tau by T. Now let us substitute the values. So here T tau is known, Ti is known, Ta is known, and the time constant is known. Only unknown will be tau. So it is 90 minus Ta is 20 degrees Celsius divided by 550 minus 20 degree will be equal to e to the power of minus tau divided by 77.68. Now calculate the value of tau. So the left hand side it is 0.1321 will be equal to e to the power of minus tau divided by
157.25. 157.25, sir.
okay. So now what I'll do is I'll take e to the other side. So it becomes ln of 0.1321 will be equal to minus tau divided by 77.68. So if you calculate this, tau will be equal to
157.25.
157.29 seconds.
25.
25, sir.
25 seconds. So this is the time required to reach 90 degrees Celsius if the cooling starts at 550 degree Celsius. That is the solution for A. Now we have another case where we need to find out the instantaneous heat transfer rate if time is 120 seconds. So for this case, let us solve this. So B, we need to find out Q instantaneous if tau equals 2 minutes or 120 seconds. So now we have two equations for Q instantaneous. Q instantaneous or Q tau.
MCP dt by d tau.
Yes, MCP into dt tau divided by d tau, which is also equal to h into A into T tau minus Ta. Okay, we have these two equations to find out the instantaneous heat transfer rate, where A will be the surface area of the object. So here it is the surface area of the sphere, and T tau is the temperature of the at the surface at 1/20th second. So first let us calculate the temperature. So we have the above equation. T tau minus Ta divided by Ti minus Ta will be equal to e to the power of minus tau by T. We know T, we know T tau. Sorry, we don't know T tau, we know tau, and we know Ti and Ta. So we need to calculate the temperature at 1/20th second. So I'll write T tau minus 20 divided by 550 minus 20 will be equal to e to the power of minus 120 divided by 77.68. Now calculate the temperature.
133.07.
So T tau, that is temperature at 1/20th second, is 133.37. Okay, 07 degree Celsius.
Sir, ಇದು ಓಟ್ ಸ್ಟೆಪ್ ಅಲ್ಲೇ ಟಿ ಟೌ ಐತಲ್ಲ ಮಧ್ಯದಲ್ಲಿ ಯಾಕೆ ಮಾಡ್ತೀವಿ?
T tau for the first case is different because only time is 157 seconds. Now the time is 120 seconds. So the temperatures will be different at these two time.
Okay, sir.
In lump system, the temperature depends only on time. So
Okay,
as the
sir.
time changes, the temperature also changes. Now we have T tau. Now we need to calculate area. Or I'll write directly here itself instead of calculating We will write the equation here itself. What is the surface area of a sphere?
4 pi r square.
Yeah, it is 4 pi r square into t tau minus Ta. So now h is 120 multiplied by 4 pi multiplied by radius is 7.5 into 10 to the power of minus 3 whole squared into 133.07 minus 20 degree Celsius. So what is the value of Q instantaneous or Q tau?
9.590.
9.590.
590.
That is the instantaneous heat transfer rate. Okay, here in this problem, in the last one we had mild steel sphere, but here we have an aluminum sphere that is weighing 5.5 kg. So it's not a small sphere. Since the density of aluminum is lesser, 5.5 kg sphere will be a very large sphere in diameter, and its initial temperature is 290 degrees Celsius, and that is suddenly immersed in a fluid which is at 15 degrees Celsius. It can be water or it can be air, we don't know that, but they are saying it's immersed in a fluid at 15 degrees Celsius. The convective heat transfer coefficient is 58 watt per meter square Kelvin. We need to estimate the time required to cool the aluminum, that is the sphere, to 95 degrees Celsius. Initially it was at 290 degrees Celsius. From there to 90 degrees Celsius, what is the time required? That we need to estimate. And here he is directly asking you to calculate using the lumped capacity method of analysis, or the lump system analysis method, and he has given the characteristics of aluminum, that is density, specific heat, and thermal conductivity. So since here they have asked you to directly calculate using the lump system analysis, there is no need to find out the Barrett number. If the Barrett number is greater than 0.1 also, you have to go with lump system analysis, because that is what they have asked in the problem. Okay, but to calculate the time constant, we need to calculate characteristic length, LC. So here in the problem, they have given the weight and they have given the density. They haven't given the volume or radius or any other thing. Okay, so with the help of the weight and density, we need to calculate the volume. Once you know the volume, using the volume equation, we need to find out the radius. So once you know the radius, then you can calculate the characteristic length. That is the only difference in this problem. Except that you just have to estimate the time required, which we have done in part A of the previous problem. So first, let us list out the data here. So the data that are given here are, we have aluminum sphere weighing, that is mass of the sphere, I'll use small m, it is 5.5 kg, and its initial temperature is 290 degrees Celsius, and it is immersed in a fluid at 15 degrees Celsius, that is Ta is 15 degrees Celsius. The convective heat transfer coefficient H is 58 watt per meter square Kelvin. Now we need to find out the time required, that is tau, if T tau is 95 degrees Celsius. So here I have given the properties of the aluminum, that is density is 2700 kg per meter cube, and specific heat they have just given it as C, it is Cp or C, you can call it as Cp, as 900 joule per kg Kelvin, and thermal conductivity is 205 watt per meter Kelvin. The other thing is, since we are dealing with aluminum, which has a very good thermal conductivity, we can assume that the temperature within the solid or within the sphere will be uniform. If the thermal conductivity value is low, then the only way to find out whether it's uniform or not is with the help of Barth number. But anyway, we will also calculate Barth number for this problem so that we will know what is actually happening. Okay. So now these are the data given. So we need to find out the time. So now let us go for the solution. First, we need to calculate characteristic length LC. The LC is given by R by 3 for sphere. If it is R by 3, then we need radius. That is nowhere mentioned here. So we have the mass and we have the density. We know that rho is given by mass divided by volume. So we can calculate the volume with this. So volume will be equal to mass divided by density. And for a sphere, the volume is 4 by 3 pi r cube. So from this, we'll be able to calculate the radius. Once you know the radius, we will calculate the characteristic length LC. So now, let us calculate the radius first. So using this equation, I'll substitute mass as 5.5 divided by density is 2700 will be equal to 4 by 3 pi into r cube. To calculate the value of radius r,
Zero point zero seven eight
0.078
7 8.
meters or 7.8 centimeter or 78 millimeter. So that is the radius of the sphere. Now calculate the characteristic length. LC will be equal to R divided by 3, which is 0.078 divided by 3.
0.026.
0.026 meters. That is the characteristic length. Now let us also calculate the Barth number. We know H, we know K, so we can calculate the Barth number value, although that is not required in the problem. Barth number BI will be equal to H into LC divided by K, which is equal to 58 into 0.026 divided by 205. What is the value of Barth number?
7.35 into 10 power minus 3.
7.35 into 10 to the power of minus 3, which is less than 0.1. So we can go with the lump system analysis. So now let us go with the lump system analysis. For a lump system analysis, we know that T tau minus TA divided by, for lumped system analysis, know that T tau minus TA divided by Ti minus Ta will be equal to e to the power of minus tau divided by T. Let us calculate the value of T. Now let us calculate the value of T, thermal time constant. Thermal time constant. Rho is 2700 into Cp is 900 into Lc is 0.026 divided by H is 58.
1089.31.
1089.31 seconds. This is the thermal time constant. Now let us go back to this equation and calculate the time required. So the final temperature is 95 degrees Celsius minus the fluid temperature is 15 degrees Celsius divided by initial temperature is 290 degrees Celsius minus fluid temperature is 15 degree. That will be equal to e to the power of minus tau divided by 1089.31. So calculate tau.
1345.01.
1345.01 seconds. There is a very large value. Can we convert this into minutes? Divide this by 60.
22.41.
20.
22.41.
2.41.
Minutes. If the time value is very large in seconds, then convert it into minutes or hours. Okay, this is the time required to reach 95 degrees Celsius.